In this presentation, we're going to look at continuous optimal control. Now, there are three approaches. One is a Lagrangian method. Second is a Hamiltonian, or best known as the Pontryagin maximum principle. And then there's dynamic programming, which we will not cover in this presentation. And of course, there are the issues regarding continuous time versus discrete time and deterministic versus stochastic models. And we will look at those differences a little later on. The continuous time dynamic optimization problem begins with maximizing some function r, which is a function of a control variable x, a state variable x, a control variable u, and time. The time derivative here indicates that this function might change with time, and we will be looking at functional forms that do not change with time. So we want to maximize this over a period. We want to maximize this function through time from current time, 0, to some future time, big T, subject to the constraint that the change in x at any instant in time is a function of the state variable x, the control variable u, and again time. And the control variable and the state variable are functions of time as well. We also have an initial condition that x at time 0 is x subscript 0, and that x at the terminal time t is given by x subscript big T. And of course, we want that the control variable and the state variable are positive at all times, or at least non-negative. Now, I should point out that we've talked about the state variable and the decision or control variable, but there's also a co-state or adjoint variable lambda, which will be introduced. So let's look at a resource management example similar to something that you'll find in the textbook. Here we have that revenue, net revenue if you like, is a function of the state variable and the control that is imposed, the decision that is made, and it's equal to price times harvest, and it's harvest that's really the decision variable here, minus the cost, although here we also have that cost as a function of the decision that's being made. P is the price, H is harvest, U in this case will be effort. So harvest is a function of population, perhaps population density in the case of fishery, and that would be measured in kilograms. It could also be the number of wildlife per square kilometer or something like that. Effort is what's devoted to harvest, and cost is the function of effort. The equation of motion, or the dynamic constraint, is given by x dot, where x dot is equal to the first derivative of x with respect to time. And we assume that that function f is a function of the growth, g, which is a function of the stock, minus the harvest, which is a function of the state variable, the stock, and the decision as to how much to harvest. So the change in the wildlife stock is a function of growth minus harvest. Now, the most common functional form that is used in the economics literature is the growth function. X dot is a function of g, where g is some intrinsic growth rate. X is the stock, and then all of that multiplied by 1 minus x over k, where k is the carrying capacity, and often we set k is equal to 1. The harvest is a function of the effort u, the state variable k, how much stock there is on the ground or in the ocean, and q is a catchability coefficient. K is the carrying capacity of the environment. So what happens is we see that the population grows according to this dark line, and it then reaches a carrying capacity of k. If it goes beyond k, then natural factors will cause the population to decline, and if it's less than k, natural factors will cause the population to increase to k. If we introduced harvest, of course, then the population would decline according to this growth function. Not this one, but the one on the previous slide, where we subtract the harvest from the growth. All right, now, it's unrealistic to think that a population would, the moment it increased beyond zero, that it would go on its own to the carrying capacity. Rather, we often specify what is known as a minimum viable population, denoted by K0 here, and we then use a functional form which looks like this. Now, this functional form is different from the one that you'll see in the textbook. So what we have here, and we'll come back to that, what we have here is the black line is your standard logistics growth function that we use, and the red line is some kind of a dispensational growth function, the dispensational part being the part that once you get below the minimum viable population, the population will go to zero regardless of what you do. Now, if we impose on this diagram the standard equation that is used in the textbook, this is equation 3.1d on page 77 in the textbook, which is referred to as the critical dispensation equation. All right, the blue line, and again, notice that this critical dispensation refers to the fact that you've got a minimum viable population. Then we find that this blue line goes up very quickly and then comes down, as opposed to this other critical dispensation model, given by the red line, all right, that has a different functional form altogether. If you're interested in looking at these functional forms in more detail, you should look at pages 76 and 77 in the text, or including the diagram on page 78, figure 3.2, where 4 net biological growth functions that we'll talk about later in the course are plotted. Now we want to convert the above problem to a Lagrangian form. The continuous time Lagrangian looks very much like the Lagrangian does in discrete time, and that is that the Lagrangian is a function of the state variable, the control, the co-state variable or adjoint variable, time, and it's given by the objective, which was r, minus lambda times x dot, the left-hand side of the equation, the dynamic constraint, minus the right-hand side, all right, the growth, which was the growth function, which was given as a growth function minus harvest. The dynamic equivalent of a Lagrange multiplier is that lambda, and it's interpreted as a shadow price. We solve this particular Lagrangian using the Euler-Lagrange conditions on the next page, where they're given as the partial of the Lagrangian with respect to the state, the control variable, minus the derivative with respect to time of the first partial derivative of the Lagrangian with respect to the control variable dot, in other words, du dt. And it's set to 0. The same thing is done with the state variable, and the same thing is done with the co-state variable. These are your Euler-Lagrange conditions. Now we know, if you look back at this Lagrangian, and you take the derivative with respect to u dot and lambda dot, there is no u dot on the right-hand side, so it's equal to 0. There's no lambda dot on the right-hand side, so it's also equal to 0. But there is an x dot on the right-hand side, so we've got a minus lambda, which is shown right here. So dl dx dot is your minus lambda. Then upon substituting these 3 equations into the above 3 equations, we get the following 3 conditions. that the first derivative of the Lagrangian is equal to 0. The negative, the first derivative of the Lagrangian with respect to the control variable is equal to 0. The negative of the Lagrangian with respect to the state variable is equal to lambda dot, which is the co-state variable. And the third condition is that the partial of the Lagrangian with respect to the co-state variable, the shadow price, is equal to 0. Now, it's important to recognize that the first condition is referred to as the maximum principle. The second condition is the co-state equation, and the third condition is simply the state equation, or the equation of motion, namely it's the equation of the constraint, the dynamic constraint. Now recall that our Lagrangian was given by this function here, r minus lambda, and then in brackets x dot minus f, which we can rewrite as r minus lambda x dot plus lambda f, and we define the Hamiltonian as h is equal to r plus lambda f. And as a result, the Lagrangian is simply given by the Hamiltonian minus lambda x dot. So then all we need to do is restate the above necessary conditions, and these then become the partial of the Hamiltonian with respect to the control variable is 0. The negative of the Hamiltonian with respect to the state variable is equal to lambda dot, and the partial of the Hamiltonian with respect to the co-state variable is equal to x dot. So these are known now as the maximum principle, the adjoint or co-state equation, and then the state equation or equation of motion. So all you really need to do is kind of memorize these conditions, and then you can solve many of these problems. If r is concave in the control variable and h is concave in the control variable, then we have a maximum condition. So dh with respect to the control variable equals 0 characterizes a maximum. If r is convex in u and h is convex in u, then the partial of the Hamiltonian with respect to the control variable being 0 characterizes a minimum. The general approach to finding a solution is to estimate the co-state variable and define a steady state. So we define the optimal solution with stars. All right, so x star, u star, lambda star are the optimal values of the three variables. Now, the transversality conditions, these are your endpoint conditions, are given by these conditions here, these points. If it's a fixed terminal time problem, if the stalk is unconstrained, so in other words, there's no constraint on the stalk at the end. For example, at the end you may have it that there are fish in the ocean, but it just simply doesn't pay to take more out. Well, then you find that the lambda, the shadow price at that time, at the end of the time horizon, is equal to 0. If the Lagrangian, or the shadow price, is greater than 0 at that time, then you can make a profit by further exploiting the stock, if there is stock available. So generally, if the stock is limited, then the shadow price at the terminal time is greater than 0, and therefore you expect that the stock is equal to 0, the terminal time stock, or sometimes it could be positive, but it just simply doesn't pay to remove any more of the fish or whatever you're harvesting. So that's the second condition. Suppose that's the case, then from the Karush-Kuhn-Tucker condition, the KKT as we call it, you find that the lambda has to be greater than 0, greater than or equal to 0, and that the condition xt, capital T minus xt times lambda t has to be equal to 0. So in other words, x, the amount of stock you have at the end of the time horizon, is some value x sub capital T, or in which case lambda has to be equal to 0 at that time. And we refer to that in condition 3 as the scrap value, and that means that the salvage value x subscript big T is not equal to 0, and then what we do is we find that the shadow price is simply given by the derivative of the salvage value with respect to the state variable. And finally, when you have a free terminal time, for example, if you're exploiting a non-renewable stock, then a condition has to be that the Hamiltonian at time t, at the end time, is equal to 0, and in which case the end time condition is variable. Now, when you have discounting, economists discount, what we want to maximize now is the discounted value of net returns, which is given by this equation here. Again, we integrate from 0 to big T, but now we've got this element here, e to the minus RT, that we have to deal with. In this case, what we do is we define a current value Hamiltonian, which is given by HC, and we'll drop that C in the future, which is the Hamiltonian that we've worked with till now, multiplied by e to the RT, which implies that the first derivative of that current value Hamiltonian with respect to the state variable is equal to e to the power RT times the first derivative, the first partial derivative of the Hamiltonian with respect to that state variable. So HC, the current value Hamiltonian, is simply the compounded present value of the Hamiltonian that we had defined previously. Now the co-state variable becomes, in this case, phi dot is equal to R phi minus partial of HC divided by, with respect to X. We're going to change that. What we've done here is we've used phi instead of lambda, and we're going to go back and restate that using lambda and also dropping the C here. But this then is the new maximum principle in the case of discounting. And the other equations remain the same as before. So if we look at the fisheries management problem, which is done in chapter 3 of the textbook, harvest is a function of effort, U, and the density of fish, X. The objective is to maximize discounted returns, net returns over the period from time 0 to time big T, and it's stated as follows. So here we have the price times the amount of harvest, and minus the cost, which is a function of effort, and of course harvest is a function of how many fish there are, and effort, and the constraint is the dynamic constraint given by X dot, so the growth of the stock minus the amount that's harvested. The current value Hamiltonian is simply the price times the harvest minus cost plus, and I'm still using phi here, the shadow price G of X minus HXU. Notice that I've dropped the X dot from this particular expression down below. All right, when we take then the necessary conditions, the first necessary condition is the maximum principle, which is that we take the derivative, the partial of the Hamiltonian with respect to the control variable, set it equal to 0. We rearrange the equation as follows, so that the price times the partial of the harvest with respect to effort minus partial of cost with respect to effort is equal to the Lagrange multiplier, or in this case simply the multiplier with respect to multiplied by the partial of the harvest function with respect to effort. And we also find that lambda dot, or in this case phi dot, the co-state variable, is equal to R times phi minus the partial of the Hamiltonian with respect to X. We rearrange that and we get this more complicated expression which has meaning. Let's first look at equation A, which states that the marginal benefit of the current harvest of fish or wildlife. That's the left-hand side. All right, so that means a marginal amount of effort gives a certain amount of harvest, which we multiply by price, subtract the cost from that, and that gives us the marginal benefit of the current harvest. The right-hand side gives us the marginal benefit of keeping those fish, if you like, in the ocean, and they have a value at some future period, and that value is given by lambda. And lambda is a discounted, or phi rather, is a discounted shadow value. All right, so if we leave the fish in place, this is the value of doing so, the right-hand side. Equation B is a more difficult equation to talk about because it gives the change in the co-state variable, in other words, in the shadow price, over time. And it's kind of like an arbitrage condition that assures that for any optimal solution, the resource owner is indifferent between the current exploitation of the resource and future exploitation. If they're not indifferent, then someone can gain by intertemporally reallocating supply. Now, the other equation that we derive is we set this x dot equal to 0, and we get that harvest, the right-hand side, is equal to what grows. So in the steady state, harvest is equal to growth. And from A in the previous slide, all right, we find that the shadow price is given by P minus C prime U. So the C prime is the partial of the cost function with respect to the control variable divided by the partial of the harvest with respect to the control variable. Substitute that expression into equation B, and we end up with this more complicated expression where R is the discount rate or the interest rate in the economy. If we rearrange that equation, we get that G prime of X is equal to this expression here is equal to R. The left-hand side of C has an interpretation. The first term, this G prime of X, is the marginal growth rate of the in situ stock. So if we leave the fish in the ocean, they grow and their value increases, particularly think of keeping price constant. The second term is the marginal stock effect that measures the marginal value of stock relative to the marginal benefit from harvest. And these two terms together, the left-hand side together, are the internal rate of return to the in situ stock and must equal to the rate of interest or the rate of return available elsewhere in the economy. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.